Many people think escalators work like this. Two wheels drive a chain, and steps are attached to the chain. But at the top, the steps would tilt forward, making it hard to get off. The same problem happens at the entrance where steps tilt upward. Since both ends cause trouble, designers tried extending the escalator at both ends, but that only made things worse. The extended sections became almost impossible to walk on. These, however, are the two correct transmission designs used today. Let's take one apart. First, it's powered by an electric motor, only about 50 kilowatts, but spinning at 1,000 revolutions per minute. The motor transfers torque to a large reduction gear, which drives the main chain wheel. The drive chain is fitted with special small rollers that pass smoothly through the gaps in the sprocket teeth. Each roller also secures a step to the chain, while allowing it to rotate freely around its axis. Behind each step sits a second wheel, rolling along a separate guide rail. On the sloped section, the rail and chain overlap. At the top, they separate but remain parallel. As the large sprocket turns, each step flips over, travels along the return path, and rejoins the main track at the bottom, repeating endlessly. Have you ever noticed that the handrail moves faster than the steps? That's intentional. A friction wheel drives the handrail. Over time, friction wears the wheel smaller, causing the handrail to lag. To compensate, manufacturers preset the handrail speed to be 2% faster than the step speed. That's why your hand slowly slides forward when you ride. The biggest safety concern is the gap between steps, especially at the entrances and exits, where clothes can get caught. To fix this, designers added a triangular zone at the end to guide passengers off to the side, but side exits caused new problems. Passengers lost balance and twisted their ankles. The best solution is grooved steps that interlock with a comb plate at the landing. Even tiny objects get lifted out instead of trapped. Modern escalators now use AC induction motors that can instantly switch between motor and generator modes. When enough people ride down, their weight turns the escalator automatically, converting gravitational energy into mechanical motion. That motion spins the motor's rotor faster. Once the rotor exceeds the magnetic field speed, it induces an electric current and creates an opposing magnetic field. This magnetic resistance slows the rotor while turning the motor into a generator. The recovered electricity feeds into the building's internal grid, powering lights, systems, and even the upward-moving escalator. In crowded places, down escalators can recycle massive amounts of energy, making the system both safe and self-sustaining.